All right. Okay, so we will do, so today's class we will cover, we'll wrap up our study of Huffman codes, and then we will look at minimum spanning trees. We will go over some, so we'll get back into graph algorithms. So we will go over definitions. As usual, when we encounter a problem, we try to, before trying to solve it, we try to understand some properties about it. So we'll spend some time looking at properties of spanning trees, and then if we have time, we will complete one algorithm for the problem. We're going to look at two algorithms for the problem in this class. Okay. And then we'll have to put it at the end of the class. So last class we defined Huffman codes, and we pretty much set the stage for the algorithm. So let me just state the problem first again. So the Huffman coding problem is what you're given is an alphabet and the alphabet is what is A, and for every letter in the alphabet we have a frequency. For every letter in the alphabet, we have an integer frequency. It doesn't matter that this is an integer, but let's do this. And what we need to find a prefix-free code. And recall that a prefix-free code is specified by a tree, a binary tree, such that minimizes the following quantity, which is called the cost. Summation all x belongs to A of the frequency of x times the depth of x in the tree. Okay? This is okay, and recall that in the tree every every letter is a leaf in the tree. So that's the problem. You want to find that tree such that if you add over all the letters of the alphabet, their frequency times their depth, you will get the minimum possible. Okay? So we are given, all we are given is the alphabet with the frequencies for each letter of the alphabet, and now we have to build this tree. So one of the first things we will argue, and we mentioned this last time, let me call this as greedy choice property. That is, that in an optimal tree, or there exists an optimal tree, in which the two least frequent characters are siblings and at the lowest level. The two least frequent okay? And we'll prove this. Okay. Most of the proofs in this line is, and similar to what we did for the task scheduling problem or the interval scheduling problem, they all have this flavor of an exchange argument. Okay? You are arguing that the greedy, your choice is in the optimal solution. Well, then you say, okay, let's suppose it's not. Let's suppose the optimal solution looks differently. Well, if the optimal solution looks differently, then you can make a change to the optimal solution to make it look like this without increasing the cost. Then you would have proved this. Okay? So, suppose T star is an optimal tree. And suppose x and y are the least frequent characters. Okay? What do you want to show? That x and y are siblings at the lowest depth, maximum depth, sorry, the lowest level. X and y are siblings in T star. Right? That's what we are trying to show. If x and y are at max depth and siblings in T star, then done. Agree? Otherwise, we are going to do some change to T star. So let's look at what T star looks like. So otherwise, this is what we are going to do now. Okay, what does T star look like? It's the key thing we observe, the key argument, the key property that we're going to use about T star is T star has two leaves at maximum depth, which are siblings. So consider any tree that is supposedly the optimal solution. Okay? You agree that there is some leaf at the maximum level. Okay? So let's say this is a leaf at the maximum level. Let me call this leaf alpha. This is the maximum level. There is no other leaf higher than this. So let's look at its parent. So the claim is that this should have a sibling. Okay, why? Suppose it has no sibling. Then what can you do? You can move alpha one level up. And if you move alpha one level up, what will happen to the overall cost? It will decrease because the depth will decrease for alpha. Right? So at the lowest level, alpha needs, if alpha is the leaf at the lowest level, it needs to have a sibling. So let beta be the sibling. So this is T star. Alpha is a leaf at the lowest level, beta is another leaf at the lowest level. We want X and Y to be there, not alpha and beta. Okay? But of course X and Y are there somewhere, right? Let's say X is sitting here. Let's say Y is sitting here. Okay? Of course, it's also possible that X might be alpha, but Y might be sitting there. It doesn't matter. Let's just picture T for a representative. So what will you do to T star to make this happen? Fine? Yeah, so move X to alpha, move Y to beta. Okay? Why is it the right thing to do if we are interested in minimizing cost? Remember, X and Y are the least frequent. Okay? So when you trade X and alpha, what happens to the cost? It can never increase. Why is that? Because you are moving a character with low frequency and moving it to a lower depth, and moving a character with high frequency and moving it to a higher depth, and moving it to lower. Okay? You agree? There is nothing, it's basically, so we can actually establish it very formally. So let's say this depth is, let's just do the one swap. So what happens to, let's say, swap X with alpha. So change in cost. What's the change in cost? What's the new cost for X? The new cost for X is, what was the depth of alpha so d of t, so the depth of alpha and T star, now F, X has the depth. Depth of X star, now alpha has the depth. Okay, this is the so the new cost of X and the new cost of alpha. What was the old cost of X and alpha? Alpha, F of alpha. T star. Everybody see that? Previous depth of alpha times frequency of X plus previous depth of X times frequency of alpha minus previous depth of alpha times frequency of alpha minus previous depth of X times frequency of X. Okay? I want to say that this cannot be positive. It can only be 0 or less than 0. Why is that? Well, you can just take things common, and this will come out to d of T star alpha. That's what you take out here. Minus d of T star X. And you are multiplying that by Fx minus F alpha. is this quality positive or negative? dt star of alpha compared to dt star of x. It's always greater than or equal to 0. Okay, so this is greater than or equal to 0. What about this? fx minus f alpha? It's always less than or equal to 0. It may be equal to 0 if all the things have the same frequency, for example. So this is less than or equal to 0. So the product of these two has to be less than or equal to 0. So this whole quantity is less than or equal to 0. That means by doing the swap of x and alpha, you have not increased the cost. And you can do the same thing with y and beta. You have not increased the cost. Okay? And so now you have a new solution which satisfies the property that you want, which has no more cost than t star, but t star is supposed to be optimal, so this better be optimal. Okay? So notice that this calculation is really almost an obvious calculation, but we're just doing it systematically to show that it works. I mean, it's an obvious calculation. If you have two numbers and if you have two things that you have to weight, you always give the higher weight to the, depending upon what you're trying to minimize. In this case, you have two numbers, fx, which is less than f alpha, then you give fx the larger value and f alpha the smaller value. Any questions about this? Yes?
Why choose two numbers? Why not one? Why not more than two?
So good. So we are trying to build this tree. So let's look at the one version. So the one version would say there exists an optimal tree in which the least character is at maximum depth. That's true, absolutely true. The same argument can apply. Okay, so the thing is, this is we are trying to build a binary tree. So if you're building a binary tree, then the way you make progress is you identify two things that you can pack together. So this is what allows you to do with two. You would be interested in doing three things at a time if, for example, you were not building a binary tree. If you were building something like a three-array tree. Okay, this is similar to one of the problems in the problem set. Okay, where you may consider looking at three things at a time. Okay? Any other questions? Okay, so this tells us that we have identified some piece of the optimal that we can try to make progress on. Okay? Now the problem is, what do you do if I tell you that these two if I tell you that you identify two characters, they have to be that this is the optimal tree, and there is this, and these are the two lowest characters, two characters which have these three smallest frequencies, and they form they are siblings. Let's say I tell you this. Then how does this help me reduce my problem, is the question. Okay. The key thing is the following. Look, so we are only interested in those trees that look like this, right? Because we have decided that x and y have to be siblings at the lowest level. Okay. So let's try to understand, what do those trees look like? What's the cost of those trees? So the cost of those trees is the same. Basically, you look at any character z, a belongs to a, is b to a. Okay. That's the cost of those trees. But each of those trees has this special thing. They always have x and y together. Okay. So let me separate out x and y. So they would all have dt of x, which is the same as dt of y. Okay, I've just separated out dt of x f of x and dt of y f of y. Okay, so what is dt of x f of x and dt of y f of y? Let me call this node z. Okay, for now. Well, dt of x is nothing but the depth of z plus 1. And what is dt of y? Depth of z plus 1, the same thing. Okay, so I'm going to write this out as plus this one. Okay? So let me look at this tree and view this tree as the following, as basically the same tree that I drew, but instead I'm thinking here of a character z sitting here. So I replace x and y by this character z. Okay, and imagine I sort of remove x and y. Okay. What is the cost of the remaining tree? Well, the cost of the remaining tree is the cost of everything. Since notice that we are only looking at those trees that have this that all have this structure. So I can view the remaining problem as all the characters are there except x and y. All occurrences of x and y have been replaced by a new character z. And its frequency is actually the sum of the frequency of x and y, because every occurrence of x and y has been replaced by z. So the remaining tree is a valid solution for the remaining problem in which z has been replaced by x and y. Now, if this tree is supposed to be optimal for the entire alphabet, the remaining tree must be optimal for the new alphabet. Because if you give me, because the difference between the remaining tree and the new tree is just this excess x of x plus xy. Okay, so let me just write this out. This is equal to, so suppose replace x and y by z. Okay, suppose you replace x and y by z, then fx plus fy is fz times the depth of z times plus fx plus fy plus this whole quantity. Okay. So we find that, so let's call this cost, this is t, and let's call this string t prime. Let's call the alphabet t prime to be a plus, so I add z, but I remove x and y. So the point is that the cost of t prime equals the cost of t. So, what is the cost of t prime? The cost of t prime is summation a belonging to a prime dt prime of a times the frequency of a, right? But dt prime of a, depth of a, every character the depth is exactly the same, The only difference is now we're going to replace the depth of x and y with the corresponding depth of z. So this is exactly the same as cos of t prime plus f of x plus f of y. Okay? So the point is that give me any tree that looks like this, we can obtain a new tree for the problem which is the same problem as the original problem, except x and y have been removed, have been replaced by z. So any solution for the alphabet A can be replaced by a solution for the alphabet A prime. The difference between the two trees cost is just the sum of the frequencies f of x plus f of y, which corresponds to this difference that we didn't count. Okay. So what this means is that if t is optimal for A, if and only if t prime is optimal for A prime. Okay. So once we identify this piece, we can now reduce our problem by saying, okay, I'm going to form a new problem by replacing x and y by z and solve for that. Once I solve for that, we can just, if you solve for that, then we get z somewhere, we'll just replace z by x and y and put it there. Okay? We will, so this together with the greedy church property will give us an algorithm, a systematic way of solving the problem. Okay? Let me move this out and so the idea of the algorithm. Find characters of the two characters of least frequency. Let's call them x and y. Make x and y siblings of each other. Replace x, y by z with frequency of z equals frequency of x plus frequency of y. Okay, so you make x and y siblings, here is 1 second, and replace xy by z with frequency of z equals this. And then find optimal for remaining problem. So you get a tree. Wherever you see z, replace it by the following. Replace z by sorry, it's too small, but I will explain. Yes?
I missed on the second line of the cost calculation there.
Yeah.
What happened to the depth of x and y?
Good. So remember the depth of x and y. Okay? The depth of x and y is exactly the depth of z plus 1.
Oh, right. Yeah.
Right? So the depth of z got added in. The only thing, plus 1 was not added in, but plus 1 is being added to f of x plus f of y. That's right. Okay? We will do an example carefully and then you'll see. Yes?
What's cost of t prime equals cost of t prime versus
Thank you. Cost of t.
Cost of t would be cost of t.
The cost of t prime is cost t minus f. So cost of t prime is the, so t prime looks like this. So t looks like this, t prime looks like this. What is the difference between the cost of these two? Well, everything here has exactly the same cost. You agree? Here we have z times its depth, frequency of z times its depth. Here we have frequency of x times its depth plus frequency of y times its depth. But frequency of x plus frequency of y is the frequency of z. The depth of x and depth of y is the same as the depth of z plus 1. So the only difference between the two costs is the fact that you have an extra f of x plus f of y here. Okay, and that's what. Okay? Okay, we will do an example that should. Okay, so let's say you're given the following characters. So let's say okay, the way I'm going to write it is, so this is the input. Okay, let's suppose these were your 8 characters. Okay, and the algorithm is really very elegant. You'll see how everything will fit together once we basically apply that rule repeatedly. Okay, so these are the 8 characters. So what do? We find the 2 characters of least frequency. Which are the 2 characters of least frequency? H and C. Okay? So when we see 2 characters of least frequency, we say, okay, we found H and C. So we put H, okay, its frequency is 1. Okay, put that number here. And then C, whose frequency is 3. And we are saying that they are going to be part of the they are going to be part of, they will be siblings in the tree, right? They are the least frequency. So what does the algorithm tell us to do? Well, now view it as if we have introduced a new character of frequency 4, okay, which I didn't say it explicitly. Replace xy by z and set z's frequency to be f of x plus f of y. Okay, so think of it as if what I have done is I have crossed this out, and introduced this new character whose frequency is 4. Okay? So what are the next 2 characters of least frequency? 4 and 9, which is f. So I make them siblings. Okay? And if I make them siblings, what do? I have a new character, and I'm removing f now. I have a new character whose frequency is 13. Okay? What are the 2 characters of least frequency now? A and D. So A and D. Is 10 and 11. And we introduce a new character of frequency 21. You remove A, you remove D. Okay. What are the two minimum frequency characters now? 13 and 15. So 15 is here. And you introduce a new character of frequency 28. What's the next two minimum? 21 and 19. 19 is G. The next are 28 and 28. And then it's created. And then you have these two. So that's your option tree. Yes.
The left side of the tree is actually stretched.
The left side of this tree is, it's not drawn nicely, but, but
The items on the left side are only 3 levels deep, but they travel the same distance as 4 levels in the right.
correct. So the left side, you have so this is not a balanced tree. Okay. So if you look at the depth of C and H, that is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Their depth is 5, while this depth is 1, 2, 3. This is only 3. So it is fairly skewed. Okay, and there is a reason for that because of the fact that if you look at, this is not a good, I'm not describing it very nicely, but basically if you look at these characters, they have very low frequency. Even after you put them together, they have very low frequency. And so these three characters together, F, H, and C together, have pretty much less frequency than almost anything else in there. So that's why you're trying to put them together at the lowest level.
So as you go, you don't connect the sides until the end, and then that's the sides with
Yeah. Yes. Now notice that this may not be the only way to build it. There might be some points, there might be multiple choices, but if the numbers are such that there is sort of a always unique ways to connect it, then there will be a unique tree that is being built. Yeah.
Actually, I have a doubt in the gradient choice proof.
Yeah.
So can the change in cost be less than 0?
So
If
so-
we
so the
reduce
change in-
cost, then was it optimal in the
Then it's a contradiction.
Yeah.
Correct. So that's how
it
the
has to be 0, right?
well it doesn't matter as far as the proof goes. So it's saying that if T star is an optimal tree, if X and Y are at max depth in the tree star, then we are done. If X and Y are not at the max depth, then we'll make this change. So one possibility is there is a change in cost is 0. We are done. If the change in cost is less than 0, then it's a contradiction. So we are done again. Okay. So that's why you can assume that an optimal tree has this property.
So if it was an optimal tree, then the only way we can exchange walk like this, and the only way that can happen is if the cost is 0.
0. Correct. Correct. So this is not. Let's see. So notice that in this example, you move 10 from here. Sorry. for example, 19 and 15, you could swap these two without any problem, right? They are both the same depth. So this is not a unique tree in that sense, but the depths, you have the right, everything is at the right depth. That's the correct. Okay. Yes?
Is there any relationship between this and here are the other data structures called like the
The heap and
Yeah.
heap and not really. I mean no. So certainly there is no relationship between this and the heap. There are other data structures that have similar structure, but not something we have seen. Okay? All right. So that was the idea, and I'm not going to go over the sort of the formal description of the algorithm, but the algorithm itself, you can see it's fairly straightforward. All you need to do is sort all the characters according to the least frequency, and then you take two characters of the least frequency, make a leaf out of them, and so initially you make a leaf out of everybody, and then you take two characters and add a new node, and you insert that into your group, and so you can maintain this in a sorted order. You can insert it using sort of binary search tree or anything like that, and then you find the two leaves, or keep a heap. That would be the easiest thing to do. So you insert this, keep a heap, take this again, take the two smallest ones, remove them from the heap, connect them together, and then insert the new thing into the heap, and then you keep doing it. So the whole thing can be completed in time and log n. If you're sorting it initially or making it into a heap initially, that's linear time, and then you're working it n times. Each time it takes you log n steps. This can be done in n log n, where n is the size of the output. Yes. Yes.
The 19 and the 50 is not at the same level. So the
19
tree,
If 19 and 15 are not at the same level, so you can't do that. Sorry.
yeah, so maybe the tree should be.
Well, not really. I mean, you can swap 19 and 28. Right. So there are a lot of changes you can make. Okay. Yes.
So is the size of the algorithm the unique characters?
Is the size of the problem? You mean this n?
Yes.
This is the, yes, so the different characters in A, yes. Now two characters in A could have the same frequency, but they will be counted as separate. Okay? Okay, good. So let's move on to greedy algorithms for graph problems. So we are going to start by So we're going to start by defining the problem. This is called the minimum time tree. Okay. So here is the problem. The problem is you're given a undirected graph, okay, G, with weights on edges. assume that they're all positive integers. Okay? So there are weights and edges. And our goal is to find a spanning tree. What's a spanning tree? A spanning tree is a tree which containing the edges of the graph, containing edges from the graph that visits every vertex, that connects every single vertex. Okay? The spanning tree of G of minimum total weight. Okay? So the first thing to observe is if you want a tree that connects every single vertex, then you want G to be connected. Because if G is not connected, you cannot find a minimum span. So our graph would be connected. Okay? The second thing to observe is that we will be focusing our attention only on undirected graphs. Okay? Because a tree, if you're looking at directed graphs, then you will have to talk about strongly connected, and a tree cannot be strongly connected. Okay, every edge has a direction, and a tree, by definition, will have edges only going in one direction or the other. So while there is a notion of a spanning tree or something like that in a directed graph, we are not going to be talking about that. So we're going to talk entirely about undirected graphs. Okay? Some other things to remember from what we have learned so far. How many edges do we have in a tree with n vertices? N minus 1. So any spanning tree you're trying to build will have exactly n minus 1 edges. You are never going to have more than n minus 1 edges. Okay? Your graph G, of course, can have many, many edges. Some other things to talk about. So let's say all the weights were 1. If all the weights are 1, how do you find a minimum spanning tree? You do BFS, you do DFS. Any tree of the graph is a minimum spanning tree. Right? If all the weights are 1, what's the weight of a tree? Of a tree that spans everybody? N minus 1. So every single tree that spans the graph is a minimum spanning tree. So this problem is only interesting when we have weights that are not 1. Okay? Okay. So let's take a simple example and then we will do some. So let's say this is our graph. Okay, and take some. Okay. Let's say this is the connected graph we are given, and those are the weights of the edges. So I want to build a minimum spanning tree here. So before trying to come up with an algorithm for it, let's just try to understand what properties can we try to establish for them. So there are two things that keep coming up, and they will keep coming up again and again. as we study more and more graph properties. One is that the notion of cycles. Minimum spanning tree does not have cycles. So a tree does not have cycles, so we have to avoid cycles. That means if you look at any cycle, all the edges of a cycle cannot be in the graph, right? So for example, if you look at the cycle 17, 19, 3, okay, EHI, clearly all these three edges cannot be in the graph, in the tree, spanning tree. So you have to decide which something you have to remove. So which one would you want to remove? 19, so that's zero. But you might say, oh, but maybe 19 is needed for some other reason. Okay? Certainly that's the shortest way to connect E and H. Maybe not, but between 19, 17 and 3, that's the shortest way to connect E and H. But, okay, but still, if you want to eliminate a cycle edge, you want to eliminate edges that the higher weighted, yes? Okay. The other thing that let's take a look at that graph. The other thing we'll look at is things like cuts. So A, B, think of A, B, C, and D on one side, and E, F, G, H, I on the other side. On the other side. Okay? There are a bunch of edges crossing this cut. Okay, what are the edges that are crossing the cut? What are the weights of those edges? There is an edge crossing 7, then there is an edge crossing 6, then 11 and 28. Okay? Now, any spanning tree has to pick one of these edges. If you do not pick on any of these edges, then what will happen? It won't span everybody. Okay? So there are two things to keep in mind. A spanning tree is a tree, so no cycles. It spans everybody, so no cuts. Okay? And those are the only two things you have to think about in terms of spanning trees. So what can you say? It should include one of these edges. You agree? Which edge would you like it to include? The lowest weight edge. Okay? So what did we say? We have two observations. If you have a cycle, you would like to keep out the highest weight edge. If you have a cut, you would like to include the lowest weight edge. And those are the two main principles for minimum spanning trees. So let's write those properties down. So one is the cut property. T is the minimum spanning tree. So let's suppose T is the minimum spanning tree. Okay, and there could be multiple minimum spanning trees. So let's pick one minimum spanning tree. T is the minimum spanning tree. Let C be a cut. Okay, and I'm going to define formally what a cut is. A cut is a set of vertices on one side and a remaining set of vertices on the other side. And when we talk about edges crossing the cut, what we mean is the edges with one vertex on this side and one vertex on the other side. Just the natural definition. So C be a cut. So the way we sometimes write the cut is S complement. S is the set of vertices on one side, S complement is the set of vertices on the other side. And neither of these should be empty. Okay, something has to be there in each side. S is not empty, S complement. So let C be a cut. cut, and let E be a minimum weightage crossing C. Okay? Then there exists a minimum spanning tree that includes this edge E. Okay? Is the statement clear? Notice that we are not saying that every minimum spanning includes it, but there exists a minimum. How do we prove it? Exactly the same way we proved the greedy choice property for Huffman codes. That is, we will say, okay, let's look at this tree, minimum spanning tree. It does not, if it includes it, great. If it does not include it, I'm going to make a change to it and fix it to make it include it and still not increase the cost. Okay, so that's one property. So let me not prove it yet. Let's put the other property down. It's the cycle property. Actually, let me use the word C for cycle. Let S be a cut. And let E be a minimum crossing S. Let C be a cycle. And let E be the maximum weightage let E be a maximum weightage in the cycle C. Then I want to say that there exists a minimum spanning tree that does not include that. Okay? Okay. So we're going to prove both of these. And once you have both of these, then there are some obvious algorithms that come to mind that we will just put. So let's look at the cut property. And a lot of these arguments are pretty simple, short arguments. They use exchange, the idea of sort of some kind of a contradiction by looking at, okay, look at an optimal solution, whether it has a property or not. If it does not have the property, then you fix it to have the property, and you show that it's achieved what you want. And often a lot of these things are explained very nicely using pictures, so we'll do so. So if we want to prove this. So let's look at a cut S as complement. Okay, there are a bunch of edges. Crossing the cut. Okay, there is one particular edge E, that is the minimum weight edge. Okay? That edge E is the minimum weight edge. So let T be any MFT. We want E to be in the MST, right? So we want E to be in T. So what do? We check, is E in T? If E is in T, then we are done. Okay. If E belongs to T, then done. Right? We would have proved already that there is a spanning tree that contains E. So E, let's say E does not belong to T. What can you say about the minimum spanning tree? If E does not belong to T, since T is the minimum spanning tree, it must include one of the other edges. Right? How can it cover both sides without having one of the other edges? Okay? So let's say it includes this edge E prime. So this is the edge it includes, E prime. Okay? If not, then there exists edge E prime crossing the cut that is in T. Okay? What can you say about the weight of the edge E compared to the weight of the edge E prime? Weight of the edge E is less than weight of edge E prime, or less than equal to. Right? E is the lightest edge, the minimum weight edge. So weight of edge E is less than equal to weight of. Good. So what exchange argument would you try to do? So you want to exchange E and E prime. The question is, can we do it? Okay. So let's try to see whether we can exchange E and E prime. What will happen if I remove E prime from the graph? If you remove E prime from the graph, from the tree, it will break the tree into two pieces. Everybody see? Do people agree or disagree or? If I remove the edge E prime from the tree, will it disconnect the tree? Not necessary. It will not. Well, it will disconnect the tree. It's not necessary that it will disconnect it across this boundary. People see that? So let's say this is the edge E. Maybe maybe this is your cut. Okay. So in this graph, let's say this is, there are two choices for E prime. If I remove E prime, it does split the tree into two pieces, but it does not split it across the boundary. Okay. So we can't simply remove E prime and add E. Okay. So let me give you another example, maybe a cleaner example. So let's say we have this is weight 5, this is weight 6, this is weight 7, okay. Let's suppose this is my graph. Okay. and let's say let's say this is my tree. No, this is not a good example. So this is the edge I'm not including. And these are possibly two other edges that are there. Okay. And then I put, let's say, this. So my tree is the following. My tree consists of this edge, this edge, this edge, okay? So that's my tree. So maybe pick some numbers for this. This is a spanning tree. Everybody see that? This is the edge that I want to add. So this is a choice for E. This is a choice for E prime. But can I add this edge and remove this edge and have a connected tree? No. So just because I have an edge E and an edge E prime in my graph, in my tree, because the tree can have multiple edges crossing the cut. Okay. Yes.
On the right, though, you're not, it's not the same picture of two connected, strongly connected components. Just the left side does.
No, no. So the graph is this whole graph. Okay. The tree that I've drawn is this. This edge, this edge, this edge, and this edge. That's the tree. You agree that it's connected? Okay. A cut is any way to separate. It's nothing to do with connected components or anything like that. A cut is just any way to separate two sets. So this is the cut.
But when you say that the left side isn't one component,
It is not. It need not be. A cut is just a separation of two things. Okay? On this cut we observe that there is an edge that has the least weight which we did not pick. And we are trying to say that, oh, we should have picked it. The point is, yes, we indeed should have picked it. In this example, we should actually add 5 and remove what? Remove 6, not remove 7. 7 is crucial. You cannot just get rid of 7. So the thing is, it's not like you can say, I'm going to add E and then I remove E prime. Okay? What you need to do is, instead of removing, the way we identify E prime is we say, we're going to first add E. What happens when you add an edge to a tree? It forms a cycle. So when you add E, it will form a cycle. That cycle has to cross a cut, right? Because just imagine you're walking along the cycle, you're going from here to here. Eventually you have to come back there, right? So it has to cross the cut. Pick that edge E prime and remove that. Okay? So E forms, adding E will form a cycle. Cycle in T. Let's call the cycle C. C has an edge E prime crossing the cut. Weight of E prime has to be greater than or equal to weight of E. So you can add E, remove E prime, and obtain a new minimum spanning tree, which is either better than the previous minimum spanning tree, which is a contradiction, or at least as good. Implies take the tree, remove, add E, remove E prime. Okay, I'm not putting the set notation, but you should get the idea. That is the main aspect. Okay? Right? Okay, so we'll stop here. And